Okay, let's get started. Today we're going to talk about metaclasses. This is one of the most confusing topics I know of. But it's very meta, as the title implies. First, we're going to review new, init, and call, especially new, because new is going to finally become important today. I've mentioned it a couple of times, but today new actually comes back. And then we'll go over metaclasses, several uses of them, and then we'll do some comparison. First, though, we're not going to do group coding today. I hate to say it, but no group coding today. It didn't come up with anything. And so, since we're not doing group coding, feel free to close your computer. If you don't want to close your computer, if you have a test going on right now and you have to that's totally fine. But this is a really confusing topic, and so it's gonna hurt. It's gonna hurt, and it'll be easier to think about it if you don't have your computer up. So it's up to you, though. I'm not gonna make you close your computer, but I'll just be very disappointed. That's all. I'd love to have just an hour of really zen metaprogramming. So there's a lot of really confusing things here. So ask questions. Not every slide is going to make sense here. Okay. So first, new, init, and call. We talked about new on the first day briefly, and then it hasn't really come up again. So I want to talk about it again here. When you create an instance of a class, when you say A equals person, and then you pass in the name, whatever. Well, we know that init gets called, right? Because that's the constructor that you write. Whenever you want to write a constructor for a class, you write init, and you populate the fields, and that's the constructor. But you might remember that actually new gets called first. You don't have to always override new to create a constructor, but it's there, and it will be called first. And what new is responsible for making self. So you'll remember, init takes in self, because it's a non-static method. And so when init takes in self, you might ask, where did self come from? Well, it comes from new. New returns self. Now, if new creates self, what does it take in? You might think it's just a static method. And it basically is, but it's actually what's called a class method. This means that it takes in the class instead of self. So there's actually more than just static and non-static methods. There's actually a third type. It's called class methods, and they take in an instance of the class as that parameter. So you can think of this as basically static, because it doesn't have a reference to self. So there's no non-static reference here. Class is going to be the same no matter what we're constructing. But it takes in this instance, and that actually becomes useful. Another thing to note is that new takes in the same parameters as init. So just keep that in mind. Both new and init are inherited from object. So all classes have a new and init. We usually override init, but we don't usually do this. Why might you want to override new? Does anyone have an idea?
To do meta things.
To do meta things. Yeah, that's pretty accurate. So here's something we could do. If we're overriding new, we now have the ability to make self. So one thing you could do is maybe you could write a class, for example, where it refuses to actually construct new instances if you pass certain parameters in. So maybe if you pass in, let's say you make a person, A, and then you make another person, but with the exact same name. What you could do is, in your new method, you could keep a class dictionary of all the instances you've made so far. And you could notice that, wait, we already made a person with this name, so instead of returning a new self, return the instance of person that we already made. That's something you could do with it by overriding new. If you overrode new, you could change the rules for creating instances. And then if you did that, these would be the same instance. If you did equals equals, They wouldn't just be equivalent, they would be the same instance because we overrode new. And new, instead of creating a new instance, just returned the one that already exists. Does that make sense? So that's something you could do with new. Oh, and then there's call. Call is not inherited from object, which means it's optional. We implemented call, and what did that do? It made our instances callable. It made basically instances of our class functions. And it takes in self, it's non-static, and it can take in whatever parameters it wants. It's not related to new or init. So, now that we've reviewed that, let's get into the meta. There's this function in Python called the type function, and we've actually been using it a lot. Every time we want to check what type something is, you call type. So if we say like type of 1, it'll get int, right? But there's actually another way to use the type function, and we're about to see that. So let's say we're making a person class, standard person class, takes in a name and an age. Oh, that's a typo. That should have taken in an age parameter. And then when we call talk, it'll print out the name. Now if we make a person, we call talk, we get what we expect. Basically, your standard person class. And when we call type on that instance, we get person. But the catch is, just like functions, in Python, classes are objects. So, at the very beginning I said everything in Python is an object. And that was true for functions. Functions were objects. Turns out that's also true for classes. Classes are also objects. And just like with functions, there's another way to write classes. So here's the other way. We could define the init method, but notice we're not inside a class definition right now. We're just defining a method. A function. This function takes in self and name. We don't know what self is. We're not in any class. So self is kind of just some name. And then we do exactly what we did in the class. And we've got a talk method also. Now what we can do is call type again. But this time, if we pass in 3 parameters, instead of calling this version of type, it'll call another version of the type function, which creates a class. So if you call type with 3 parameters, it'll create a class. It'll create a new class. So there's 2 usages. If you pass in one thing, it inspects the class. If you pass in 3 things, it makes a class. And what did we pass in here? We passed in the name, just like the name right up there, same name. We passed in a list of base classes, just like how we can do up here, right next to the name. And then what's the last thing we pass in? A dictionary of all of the contents. So what you can maybe visualize here is that everything inside of this class definition, you can basically think of as a dictionary, mapping from these names to these methods, and that name to that method. That's exactly what we have here. We have a dictionary mapping the name of this method to the actual method we implemented. Now, when we do that, we can basically use alt person like we would any other class.
What happens when you wrote alt person equals type alt person?
Yeah.
What those match right now, but what if
they don't match?
Which one would be the one to use?
Good question. So basically, let's say we called this foo, but we still passed in the alt person here. Then when we make an instance here, we would use foo, right? Because that's what the variable name is. We would say foo.
So what's the purpose of the alt person?
Well, when we call type of B, we would get alt person.
Okay.
So there's 2 things going on here. There's the name of the class, alt person.
Yeah.
And then there's the variable through which we're referring to that class. And they don't have to match. Yeah. Okay. So this is cool because now we've converted class definition into a function. And that means we can do dynamic class construction. So here's one possible use you could have for this. let's say we have another person in class, but this time we take in a first name and a last name, okay? And then we set the name field to the concatenation of the two. That kind of makes sense. And then our talk method says, I'm this name. Now we're going to define a class method. So this is what I was talking about earlier. Our class method is basically static, except that it also takes in an instance of the class. The class itself, basically. Sorry, not an instance of the class. That would be an object. It takes in the class. So this variable, CLS, will be capital P person. It is the same thing. So, and we take in a family name, and then we're going to define an inner function. And this inner function is going to take in self, first name, and then it's going to pass the family name in as the default argument for last name. And then we're going to call init on the class with self with that first name and last name. And then we're going to return the type of that last name, subclassing class, and mapping init to that new init.
So is CLS like just the default like self? Can that be anything?
Yeah, you can actually name this variable anything. It's just like self in that way, except it's convention to use CLS here because it's not an instance of the class, it is the class.
Okay.
Yeah.
And so the at class method, is that just what points it at person?
Well, if we didn't say at class method here, then self would be passed in for class.
Okay.
So if you say class method, and then the class will be passed in,
And
which
the
is why I
class
named it
method
class.
is a fixed keyword then?
At class method is a built-in decorator.
Okay.
Yeah. Uh-huh.
So why do we have a function base there? Why don't we just override new?
Why don't we override new? Well, so what we're doing here is we're actually making a new class, a completely new class. So if we overrode new, what we would do is change the way instances are made. But this is separate. This is making a whole new class. And we're returning that class. And our new class has an init function where the last name has a default argument. And the default is the family name. So now if we use this, we've got Steve as a person, Steve Jobs. And Steve says he's Steve Jobs. Now we can say fam equals person dot make family Paddock. Okay? That's my last name, by the way, in case you didn't know. I'm not just into watches or anything. No relation, by the way. I'm not related to. And so now when we call this, what is fam?
Equivalent to person.
Equivalent to person?
Equivalent to the class person.
A new class.
It's a new class which inherits from person. Right? We've made a new class. It inherits from CLS, which is this. So fam is a new class with the name Paddock, which inherits from person and has this new init method. So if fam is a class, that means we can call it. We get me. And now if we say me.talk, I'm Max Paddock. You'll notice I didn't have to pass in my last name here. We passed it in when we made the family. And everybody in the family, by default, has that last name. Do you see how that's useful? Now, if we inspect the type of Steve, we get person. The type of me, we get Paddock. So this is dynamic class creation. And it's possible because class creation is actually just syntactic sugar around a call to the type function. If we check if is instance, it works how we expected. I'm a person, and that's true because Paddock inherits from person. And if we check if Steve is an instance of fam, that's false. Steve Jobs is not a Paddock. All right. I've actually been lying, though, because type is not a function. Can anyone guess what type is? That's also true. Wait, functions are objects, so... A class. Type is not a function. It's a class. All right, so here, we can see that here. If we call type on 42, what do we get? Int. What if we call type on int? Type.
What?
Type is a class. Okay? It's the class for all classes. Remember, I said at the beginning that classes are objects. But if classes are objects, that means they have a type, right? What's that type? It's type. It's the type of type. Type.
What's the type of
It's the type of type of type of type.
This is like
It's type.
call.
Is type an instance of type?
No.
Yes.
So it inherits from itself.
Yes. Type inherits from itself.
It's like a grandfather thing.
Yeah. Okay, so now we know. Yeah? Uh-huh.
Doesn't type eventually have to be an object?
Type is also an object. Type is
just a type first.
type is a type and an
So
object.
when is it an object though? It's types all the way down.
But they're also all objects all the way down.
What came first?
Okay? Okay. Do you see why I wanted you guys to close your computers? If you like blink for a moment, it goes by. This is so confusing. But what's really going on here is basically classes are objects, but objects need to have a type, right? Well, that type is type. But wait, if type is a class, can we subclass it?
Probably.
Yeah, and that's what a metaclass is. Metaclasses are subclasses of type. Technically, type is also a metaclass. All right, so let's just see one. Let's just try it. Let's try inheriting from type. First, I'm going to import the debug decorator class. Right? So we did decorators last week. We made a decorator called debug class, and it's a decorator where you can decorate a class, and it'll just print out whenever any method of that class is called. And we're going to use it to be able to see what's going on when we make a metaclass. We've got a metaclass that inherits from type. We're going to define new, init, and call. Okay? And because we're wrapping these functions, our decorator is going to go in and decorate all of these, and that way we're going to be able to see when these methods are called. Okay? You'll notice that new, what's the parameter that new took in there? It's taking in meta. That is convention. All right, we're used to init and call taking in self, right? But what is self? Self is a class now. So it's convention to now, instead of calling these parameters self, it's convention to call them class. Because the instance that we're dealing with here is a class. But then new should take in something different to signify that new is actually a class method. So we take in meta. New takes in an instance of metaclass. It takes in metaclass itself, sorry. New takes in metaclass itself. And init and call take in some instance of metaclass, which is itself a class. Okay. So we're going to run this file here. We've written this file. We've declared this. And just so you know, if you run Python with the -i flag, what that means is that after it runs this file, it'll go into an interactive prompt. So we're going to run this file. And we'll see, before we even get a prompt, we're going to get decorating. Because that's how our decorator worked, right? So we decorate everything, and now we get into the prompt. And we want to try to use this metaclass so we can see what's going on. So I'm going to go ahead and define an init and a talk, just so that we have them for use later. And then I'm also going to define an adders dictionary so that we can use that adders dictionary later on too. Okay, so let's try using it. What is this? What type is it? Class. Yeah, this is a class. And we're calling the type function here. So this is just a regular class. This isn't using our meta class. This is just a regular class. of name type person, inherits from object, and has those attributes. Now if we make a meta person with our meta class, with the same superclass and attributes, we see that our meta class new was called. This makes sense because we just made an instance of our meta class. And whenever you instantiate a class, new is called. New is called first. So we get new, and then we get init. And then that's it. That's all. Call was not called. New and init were called because we created an instance of meta class. We had to call the constructor, which is new and init combined. So now we have two types, type person and meta person. Let's create an instance of type person. Call it TP. Now if we create an instance of meta person, MP, what's going to be printed out? Nothing or something? Yeah. Call. Right? We created an instance of meta class. That is meta person. But meta class implemented call, which means this is callable. So we called it, and so of course call is called. Does that make sense? Now MP works exactly how you'd expect. So what have we got here now? We've got some, basically, I like to think of these as hooks. By implementing new, init, and call in the meta class, we can hook into various points in the class creation cycle. So by implementing call, we can override how instances of our meta class will instantiate objects. By implementing new, we can change how subclasses of our meta class are instantiated in the first place. Does that make sense? We'll see some examples, but I just want to show you where these hooks are so that you know what we're doing when we override these methods later. But first, there's a little bit of syntax. Basically, what we did here is we directly called the meta class, and we directly called type. That's kind of tedious. We had to make this Adder's dictionary. It doesn't really, it's hard to tell that these methods are actually meant to be in a class. So there's another way to do this. Basically, if we wanted to make that type person again, what we can do is we can say metaclass equals type. Now if we want to make the meta person, we can say metaclass equals metaclass. And that works exactly the same way. So when you use the metaclass keyword argument in the class constructor line, that'll basically say, hey, Python, instead of calling type to create this instance, call the metaclass to create this instance. Any questions? Okay. So let's do it. So here's the first example, registering. What if we want to make a class that knows about all of its subclasses? Okay? That's not usually something we do, but it can be very useful, especially when you're writing APIs. Right? If you write an API and you write a class, it might be very useful for you as the API writer to know how many times your user has subclassed that type. So this would be one way to solve that. We're going to create a meta type, which inherits from type. We're going to call it registrar. And this class has a method. This method is non-static. It belongs to instances of registrar, which are classes. Classes that implement the registrar meta type. So any class with the registrar meta type is going to have this class method. Does that make sense? Okay. And we're going to assume that we've got this field called subclasses. We're going to append to it, just like how you would expect for a method called add subclass. And now we're going to define the init. This makes sense. We need to define init here because we have this method, this class method, and it assumes that we have the field subclasses. So we need to actually create that field first. So very first thing we're going to do is create the subclasses field. This is a field that belongs to instances of registrar. which are themselves classes. So this is a class field, which belongs to instances of the metaclass. And then for every class in this instance's MRO, basically, for every class that is above this class in the inheritance hierarchy, add this class to that class's subclasses list. So what is this going to do? What is this saying? This is saying that anytime we make a class that inherits from a registrar, add that class to the registrar. Okay. So we're going to make a class A. Its metaclasses registrar. Now we make some subclasses of A. And some remote subclasses of A. D inherits from C, C inherits from A. So we've got several layers of inheritance. I'm just following that diagram right there. And now we make E inherits. We've got some multiple inheritance. Shouldn't be a problem. Now if we say D.subclasses, notice this is a field that belongs to the class D. So it's a class field. If we access it, we get E. That makes sense. E is the subclass of D. So it works. Pretty cool, huh? This is something that you actually can do with a decorator. And it actually also, full disclosure, is already built into Python. Classes in Python actually have a class field already dunder subclasses, so you can already access the subclasses of classes. But I'm just showing you how you could do it with a metaclass yourself. And it's good to know this kind of thing because what if you don't want to just know what the subclasses are, but you actually want to perform some action upon being subclassed? This is how you can do it. Okay, here's another use case. Singletons. Who's heard of singletons? A couple people? Okay. This is a design pattern that limits the instantiation of objects. And we've actually already seen something kind of similar. This is very similar to a singleton. There are examples of singletons built into Python. So true, false, and none are all singletons. Basically, you can call the ID function in Python to get the memory address where that object is stored. We get some random memory address. We can call ID of bool1. This is a constructor for the bool class. So we're calling the bool class and making a new boolean with a truth value of 1. And what we'll see is that the ID of that new boolean is exactly the same as the ID of the original boolean. So basically, even though we just called a class, we tried to create a new instance, we failed. We got the exact same instance that already existed. So true is a singleton. You can't create another instance of true. True is always going to be the true. The ID of false is a certain ID. ID of bool 0 is, of course, that same ID. So booleans are singletons. So how would we do that? Let's create a metaclass, inherits from type. We have a class. So now this is another class field, but who does this class field belong to? Anyone? This class field belongs to singleton. So if we say singleton underscore instances, that will be okay. Before we had that subclasses field, that was also a class field, but it belonged to instances of singleton. So they belonged to different levels of class. This is a metaclass field. The previous was just a class field. So now, whenever we call an instance of this metaclass, if that class has been instantiated, if that class has not yet been instantiated, instantiate it, and then return that instance. This is it. This is the singleton design pattern. So now if we make a person, and the metaclass is singleton, we're going to have an init and a talk, doesn't matter. Now we call person. Person is an instance of singleton. And it is callable. We wrote call. And so as soon as we write this, that call method is being called. And it's going to check, is this class, which class are we talking about here? What is CLS? Person. Person is the CLS here. So is person in this underscored instances dictionary? Is it? No, nothing's in it. So this if statement triggers, and we add a new instance of this class, person, to the instances dictionary, and then we return it. So now we have an instance of person with the name Leah. We say talk. We get Leah. Leah's my sister, by the way. I use her name from time to time. Now we do the exact same thing again. Call person. We're calling person, which means that call method is being called. The class is person again. Is class in the underscore dictionary? Underscore instances dictionary? Yes, yeah. Because previously when we called this, it wasn't, and so we added it. We added an instance of person to the underscore instances dictionary under the key person. So now when we call person again, this key is in the dictionary. And so we return what's at the dictionary at this key, which was this. Do you see why that happened? Now if we make two more people, A and Z, they are the same. They're the same instance. It's impossible now to make any other person. Any questions about that? Okay, and I also want to show you what happens when you use inheritance with metaclasses. So let's say we've got a student class. It inherits from person. And it takes in a name and an ID. And it calls the superconstructor, et cetera, and a student can report. And the report is just the computing ID. Now if we make a student max, MTP 40E, that's my computing ID. What do you guys think is going to happen? Any ideas? It's definitely going to print something. Or is it? Or is it going to error? Right? Because it's possible that doing this will just return Leah again, and Leah doesn't have a report method, so it could error. But let's think about what's actually happening here. We're calling student, which means we're back up into this method. Is student in the underscore instances dictionary? No, person is, but student is not. So this will actually make a new person, and we'll get what we expect. But now if we make another student, of course we just get the original again. So singletons, when implemented this way, start anew for every subclass. But they do follow the subclasses. It's not like student isn't a singleton. What I'm saying here is the metaclass is inherited. Mm-hmm.
Does person still have type as a metaclass?
No.
Okay, so you only have one metaclass.
You only have one metaclass. Now, singleton inherits type. So the metaclass of person is not type, but it inherits from type. So it can be thought of as type. Do you see what I'm saying? Now, one interesting thing here is that I've never tried this. Metaclasses are hard to use because they're so obscure. But I believe that you can actually make your metaclass not inherit type, and then you'd start doing really weird stuff. That's crazy. But I'm not going to get into that. Okay. Warning, be careful with singletons. If you think this is cool, you're right, but it's also very dangerous. Singletons induce global state when they're not immutable. So if you want to have a singleton, make sure it's immutable, or be very, very careful. Okay, so let's kind of recap here. What's the difference between metaclasses and superclasses? Well, they both allow us to control the behavior of classes that use them. And both can, I mean, your superclass can override new. And if your superclass overrides new, you override new. And if you override new, you can do some meta stuff. But what metaclasses allowed you to do is actually change the behavior of an entire inheritance diagram. So the analogy here is that your superclasses are your parents. They give you your genetic code. Your metaclass is your species, right? We can redefine what it means to be an object in Python by changing the metaclass. And you can actually see there's some really bizarre examples of metaclasses out there. There are metaclasses that completely change what it means to be an object, where being an object is actually more of like being a variable. It's really interesting. But basically, metaclasses give us more control, but at the cost of really convoluted code. What's the difference between metaclasses and class decorators? They're actually surprisingly similar, because a class decorator can basically change any aspect of a class. I mean, you'll remember the class decorator I showed last class was the debug class decorator, which basically took every method in the class and changed it to the debug equivalent of that class. But we could have completely changed that. I mean, a class decorator could completely warp that class and change its new, change its init. But metaclasses are more powerful because they can actually change what it means to be a class. And the example I want to give here is try overriding a class's string method. Right? We've been printing classes actually a lot. And when you print a class, you get something like main dot and then the name of the class in angle brackets. But what if you actually want to print something else when you print a class? Well, you'd have to implement the class's string method. That's actually very hard to do. You might think you could just say @class method dunder string. That actually does not work. That still overrides object's string method. If you don't understand what I'm saying, that's okay, because I didn't put it up on the slide. But if you want to prove to yourself that metaclasses are more powerful than decorators, that's how you do it. Is there a question?
Yeah, but your analogy pretty much answered it.
Okay.
Can you decorate a metaclass?
Yeah. Yeah, so the analogy here is that decorators they can like change your genetic code. They have the complete power to change what it means to be an object. But using a metaclass is like just changing like evolution, period. Like it changes an entire sub-genre of Python, if you will.
So if you instantiate classes and then modify the underlying class, the previous ones will still stay the legacy version, right?
Sorry?
So if you like instantiate a person and then modify the person class, the previous person that you already instantiated will stay the same, right?
And modify the person class. I think so, but I don't know. I've never tried to do that. Try it. I mean, that'd be super easy to try. Just make a class, make an instance of the class, and then add some attribute to the class, and see if that original object sees that attribute. That's a really, I don't know.
Well, that's not my whole transmission alignment thing, where it's retroactively changing the methods.
Yeah, it changed.
So
Yeah.
I shouldn't see any changes to the class.
Well, if you change the class, then new instances will see that change.
Right.
But the question is, do old instances see the change? I think
But imagine they wouldn't, but
I don't know. Try it.
Yeah.
I don't know. Okay. Yeah, no, that's an interesting question. Okay, so we've kind of finished, like, if you will, the first unit of metaprogramming. We've covered all sorts of object-oriented metaprogramming. We started with dependency injection, closures, decorators. Now we finally got into metaclasses, which are like the most meta, mind-blowing thing I can imagine. But we've kind of we've stuck with objects this entire time. Every step of meta we've taken has been in realizing that something that wasn't originally an object actually is. But we're about to change gears. Next week we're going to do reflection. And reflection is more just kind of pure metaprogramming. In fact, it's an entire sub-paradigm of metaprogramming is reflective metaprogramming. And what you'll realize is that while it's different from object-oriented programming, it's very useful. So if you really want to take full advantage of all the meta power we've accumulated here, reflection will help you do that. And you'll notice I haven't been able to help but use reflection a couple of times in the slides the past couple of weeks. So basically just keep in mind all of the stuff we've learned and be prepared to change gears and be prepared for those gears to augment the original gears. Yeah, that's it. We've got some extra time, just a little bit. So there's actually a little bit that I left out because I thought it might just kind of derailed the scene. But you'll remember, let's see. We got to this slide here. Pretty cool slide, right? We called is instance type and type. Type is an instance of type. And some people were asking, like, oh, what does that mean? You know, what is type not an object? Is type an object? Well, that's actually a really interesting question. And so I wrote a slide about that, but then I took it out. But, oh, geez. So this might answer some of your questions.
What?
We can see that we've got the MRO of type here, and you can see that type does, in fact, inherit from object. So type is an object. Because remember, I said all classes are objects. Type is no exception. I mean, just because it's a meta class doesn't mean it's not still a class. And all classes are objects, so therefore type is an object. Is object an instance of type? Yes, because object is a class, and all classes inherit from type.
What does type.object do?
Type.
Object.MRO.
Object.MRO? The MRO of object is just object.
Is just object.
Yeah.
Okay.
Because type is not the superclass of object.
Yeah.
Type is the meta class of object. Object is not the meta class of type. It's the superclass of type. So that's why it shows up in the MRO of type, but not in the MRO. Yeah. Type is an instance of type, as we saw. Object is an instance of object, just like you'd expect. One is an instance of object, but one is not an instance of type, even though object is an instance of type. Do you see the lack of transitivity here? A lot of people think that is instance is kind of linear. It's actually surprisingly confusing once you know about metaclasses. Because you would think that since object is an instance of type, and one is an instance of object, that one is therefore an instance of type, but it's not. And this is what I was saying. A lot of people, I didn't animate these slides because they're in the appendix. A lot of people think that the is instance diagram looks something like this. As in, a list is an instance of list and an instance of object. You know, some variable max is an instance of person and an instance of object. And then all these classes are instances of type. But it's actually way more convoluted. This is what the actual is instance diagram looks like. You know, these objects are instances of their classes. But then all the classes are also instances of type, just like we expected. But they're also all instances of object, including object itself. And type, there's actually a typo because type is also an instance of itself. So there should be a self arrow here too. But just thought that was interesting. I wanted to put it in, but then I thought that might get a little confusing. So now you know. Whose mind was blown today? I think that's everybody, just about everybody. Some shaky hands over there. All right, cool. Yeah, I hope you enjoyed that. That's pretty meta. Yeah, all right, that's it. That's all I got.